When people talk about computer performance, two components come up constantly: the CPU and RAM. They work closely together, but they serve completely different purposes. Understanding how they interact is fundamental to understanding how computers actually operate. The CPU, or Central Processing Unit, is the component responsible for executing instructions. Every program, operating system task, and application ultimately runs as a sequence of instructions that the CPU processes. These instructions include arithmetic operations, logic comparisons, branching decisions, and data movement. At a high level, the CPU operates using a continuous process known as the fetch, decode, execute cycle. First, the CPU fetches an instruction from memory. Next, the instruction is decoded so the processor understands what operation needs to occur. Finally, the CPU executes that instruction. This cycle repeats billions of times per second. Modern CPUs contain multiple cores, allowing them to process multiple instruction streams simultaneously. Each core can run its own thread or process, which allows systems to handle most multitasking and parallel workloads much more efficiently. Inside the CPU are specialized components that carry out these operations. The arithmetic logic unit performs calculations and logical operations. Control units coordinate instruction flow. Registers store extremely small amounts of data that the CPU needs immediately during computation. Despite being extremely fast, the CPU itself cannot store large amounts of working data. Its internal registers and cache are very limited in capacity. That limitation is why RAM exists. RAM, or Random Access Memory, is the system's primary working memory. It temporarily stores the data and instructions the CPU is actively using. The key advantage of RAM is speed. Accessing RAM is dramatically faster than accessing long-term storage devices such as solid-state drives or hard drives. When a program is launched, it is copied from storage into RAM. Once the program's instructions and data are in RAM, the CPU can retrieve them quickly and execute them efficiently. This relationship is critical to overall system performance. The CPU continuously pulls instructions and data from memory. If the required information is not immediately available, the processor must wait. Even a very fast CPU becomes inefficient if it spends time waiting for data to arrive. This is known as the memory bottleneck. RAM helps reduce this bottleneck by acting as a high-speed buffer between the CPU and slower storage devices. Capacity also plays an important role. Each open application, browser tab, or background process consumes a portion of RAM. When sufficient RAM is available, many programs can remain loaded simultaneously, allowing the CPU to switch between tasks instantly. When RAM becomes full, the operating system begins moving inactive data from RAM to storage using a process called paging or swapping. Because storage devices are significantly slower than RAM, this introduces noticeable performance slowdowns. This is why systems with more RAM can handle heavier multitasking workloads more smoothly. Another important layer in this memory hierarchy is CPU cache. Cache is a very small amount of extremely fast memory located directly inside or very close to the CPU cores. Its purpose is to store the data and instructions that the CPU is most likely to use next. Modern processors typically include multiple levels of cache, commonly referred to as L1, L2, and L3 cache. L1 cache is the smallest and fastest, located directly inside each core. L2 cache is slightly larger and a bit slower. L3 cache is shared among cores and provides a larger pool of high-speed memory. The closer the data is to the CPU, the faster it can be accessed. The memory hierarchy therefore looks like this. Registers inside the CPU are the fastest and smallest, followed by cache, then RAM, and finally long-term storage such as SSDs or hard drives. Each layer trades speed for capacity. The CPU performs the computation, but it relies on RAM to provide fast access to active data. RAM does not perform calculations, make decisions, or execute instructions. Its sole purpose is to store information temporarily so the CPU can retrieve it quickly. This distinction is critical. A faster CPU increases the rate at which instructions can be processed. More RAM increases the amount of data and applications that can be actively available without slowing the system down. Both components contribute to overall performance, but they solve different problems. The CPU provides computational power. RAM provides high-speed working memory. Together, they form the foundation of modern computing systems, enabling everything from simple web browsing to complex simulations and large-scale data processing. Thank you for listening, and have an awesome day.